Good morning. Welcome to Krishna's class. We continue with our exploration of the advantages that you have because of the orthonormality relation or advantages of the possibility to choose orthonormal sets in the vector space or the inner product space. So let H be a Hilbert space. So let us briefly recall what we did last time. Let H be a overset. Now we have a orthonormal set Q alpha belonging to F, that is an index set where F is finite. It's an orthonormal set, therefore you have the property that equal to 0 whenever alpha is not equal to beta and U alpha equal to 1 for alpha belonging to F. Here alpha belonging to alpha beta This is the orthonormality relation. So we have an orthonormal set. Okay. Now what we have proved is the following. Okay. Given x belonging to x, where x is a x hat alpha, collection of numbers x hat alpha, these are complex numbers such that the vector u which belongs to, I can write here f, belongs to or uf equal to summation over alpha belonging to f x hat alpha to alpha. So uf belongs to mf where mf is the span of and uf gives the has the property that norm of for x belonging to minimum distance is the distance from x to the subspace now UF is uniquely determined. The interesting aspect is that we know that given a Hilbert space and a closed subspace of H, for any x, there is a vector that lies closest to the vector inside the subspace. This is something that we have proved. And the property that we have is that f minus x is orthogonal to okay. So this is the scenario that you have. So I'm just giving an x. This is MF. You take an x. So have a vector f. This is x. So that this is the orthogonal x minus uf, which is the vector corresponding to this. This is the vector. X minus uf is orthogonal to f. For that is the shortest distance from x to mf. Okay. So for any element of so uf is a unique vector such that this is the shortest distance from x to that is the theorem that we have proved. In the sense that strictly less than for every and equality only if u is equal to this is the result that we have proved. And it tells you a nice way to catch hold of this particular vector. Okay, what do we do? Suppose you have a subspace, say a finite dimensional subspace of, suppose we have a finite dimensional subspace of the Hilbert space. Okay, so suppose M is a finite dimensional subspace of H. Let U alpha or V alpha basis for be a basis for M. Now apply Gram-Schmidt process V alpha to get an orthonormal subspace, an orthonormal basis okay. See, the collection V alpha is finite. I will just put in the bracket that the collection V alpha is finite, and there are the cardinality of V alpha and U alpha. Okay. Finite, and the cardinalities and the number of elements in V alpha and U alpha are the same. They have the same cardinality, which is the dimension of the space. Dimension of now how to get hold of this minimal element? So let's so we'll put here that is the index set. Yeah? Okay. Let uh, x hat be defined by inner product of for alpha belongs to F. The vector UF is equal to sigma gives the vectoring name given by norm of F. This is the sum and substance of what we have proved last time. Now we go further and drop the condition that F is finite. Now we drop the condition that the index set that is we are not assuming A equal to F. So A need not be finite. A need not be even so we are taking the general scenario. So you have U alpha this is what you have. Okay. Now we have to make some remarks about then what do we sigma This is what we have. This is what we have to mean. So A may not be even countable. If it's countable, possibly you can write down a series, okay, and then talk about its convergence, etc. Because when it is finite, no such problem arises. So it's a finite sum, well defined. But the moment it becomes an infinite sum, see that the concept of convergence come into play. Okay, when it is uncountable, what exactly you meaning that you attribute? Okay, assume that these are just complex numbers. Now it is real numbers that you have. Alpha belonging to. So this is the assumption. Then we attribute a meaning to this sum. Okay, what do we mean by? Denotes the supremum of all finite sums alpha n, where alpha n are n elements, any distinct n elements of distinct elements of elements of it. So this is a finite sum. So that, see, what you have is, you have this one, this is what you want to work. Sigma alpha belonging to A, phi. What do? We take all sorts of sums of the type phi alpha 1, where n, of course, is any integer. So that this sum is a finite sum. Makes sense. Okay, because these are complex numbers, so this makes sense. Now you have a set that you have defined through this. So this is what you have. So you take the supremum one to n, n belongs to n. Okay. So you take all these sums and take the supremum of this. Now you see that they are all non-negative. By our assumption, they are all non-negative. Therefore, you see that this is greater than or equal to 0. Each one is greater than or equal to 0. Now, it could be possible that this sum is anyway finite, but the supremum may not be finite. Okay, that's the problem. And of course, it may not be even finite because we are assuming phi alpha, if phi alpha I equal to is infinity for some alpha I, then this may be even infinity. In that case, the supremum is essentially infinity. So you take all finite sums of this collection, or possible finite sums of this collection, take the supremum of that will be interpreted as sigma alpha belonging to A by alpha. So that is the meaning of this sum. So having done that, now we are in a position to handle the situation. Now note that sigma alpha belonging to A phi alpha is the Lebesgue integral of the function phi relative to the counting measure What do you mean by this? See, you have what is phi? Phi is a map from A to C. In general, C. Okay, but let us now consider the case where it is equal to R, where phi is assumed to be infinity. So we assume this. Okay. Now on A, so A we make a measure space. Well, how do you do that? A, PA is a sigma algebra on A, and then we define mu. Mu is a counting measure of say some subset F. Okay, is equal to the number of elements in or the cardinality. Okay, if you take that, then you see each one of this for a particular sum will become a integral of a simple function. Okay, so this will become integral of a simple function. Consequently, to take the supremum of that, this will be the integral. So, each finite sum is then an integral of the is then in fact the integral of phi d mu over f, where phi f is a simple function such that phi f of alpha equal to phi alpha for alpha belonging to f, and phi f of alpha equal to 0 for alpha belonging to. So on f takes the value phi alpha, and outside it takes the value 0. So we have this one, and what we are doing is we are taking the supreme. This is what you call integral So it's a Lebesgue integral. Okay. Therefore, so now we shall write the following. So this is which is equal to, or LP mu is what? Phi from intercept A to R. We are taking a real valued function, complex function, we can take it that way, such that integral over finite. This is the definition of LP space. Okay. Since we measure we have collection of what? Is what do you call this? A discrete function, a function from A to R. Therefore, this becomes a sequence. So, this is phi alpha, this a collection of numbers. I don't want to call it sequence because it is not necessarily. Had it been countable, I would have called it sequence. So we have, this is the scenario that is emerging. So we are now considering L2 here. So we will work with L2 mu, considering functions finite. This is what we are considering complex functions. I am taking a general scenario. If you are taking real function, then it is simply phi alpha square, right? So this is the function, and this collection is denoted by so what is L2A? So L2 mu can be identified with, that's the name that we adopted. Okay. Now you see that is a Hilbert space this is something which you can prove. At least initially you can prove that with inner product this is equal to this need not be a countable sum, but then we have a meaning way of attributing a meaning. Okay. L2A, and which implies this is L1. Okay, therefore that is defined. Now we also have the following property. Consider all phi L2A such that phi is finite except finite set. Okay, then this collection dense in so you take all those phi which are 0 everywhere except on a finite set. Okay. Such functions are L2 functions certainly, but that alone does not constitute the entire class of L2 functions. For example, you take this one, that is say phi n you define as 1 by n. Okay, then what is this sequence? This will be 1, 1 by 2, etc. This is not, here phi is not having a finite set associated with it where it is non-zero. It is non-zero everywhere. So phi is non-zero all n belonging to. Okay. So this does not belong to this collection. What I wanted to say is that the function phi n is 0 everywhere except on at a finite set of values of n. This is the collection. So you take such functions. They are all L2 functions, and these L2 functions form a subcollection of the L2 space, L2A. And what you can prove is that this collection is dense in L2. This is the density. It's a dense subspace of L2. Now we prove a very fascinating result. Okay. What does it mean? Suppose you write so we show the following. If phi belongs to L2A, then This is a fascinating result. This is almost, at most, countable. Cannot be an uncountable collection. We shall prove this. Okay. So whenever you say there's an element of L to A, whether A is countable or not, maybe even uncountable. You see that such a phi belonging to L to A is non-zero at most on a countable set of points. Okay, that's an important result. So let us prove this. We have proved. So let AM designate the set of all alpha belonging to A such that this is the statement. Then each AN is a finite set. If each AN is a finite set, then it would follow that the set of points where phi is not equal to 0 form a countable set. So we prove this first. Okay. So you take number of elements in A. So this is equal to, you take a function which is 1 at every point in A, okay, and sum up. Okay, this is equal to summation alpha belonging to AN such that n into 1 by n whole square. This is 1. So 1 counted as many times as you have elements in AN. Okay. Now this we can write as follows. Now we make use of this inequality, possible choice of phi. So this is equal to because mod phi alpha is greater than 1 by n. Therefore, we can replace this. Okay. Now this is less than or equal to . Okay, then one more line here. This is less than or equal to n square sigma alpha belonging to AN and this is finite. Okay, this I can replace by square because this one is the L2, phi is an L2 function, therefore this is finite. So this is finite. Okay. So this is k times n square. Okay. So what do you get? You get where did we start? We started with the cardinality. Therefore, consequently, what we can conclude is that the non-zero most on a on a countable set of. So that's a very interesting observation. Even if A is a uncountable collection, what you can have is this property that the function phi, if it is in L2, then it is zero, it is non-zero at most on a countable collection of. Okay, so that's the conclusion. L2A. This is the conclusion. Okay. Now what we are going to look at the fourth. Okay. Now let me just uh, tell you what exactly we are driving at. And in this process, we have to prove a lemma. So before that, let me just, so what we are going to do. This is what we wanted. So H is a Hilbert space. U alpha is an orthonormal collection of H where A need not be countable. It may be uncountable. A may be uncountable. Now U alpha is U alpha H. So we take all the finite linear combination of this. So we take denote by P the set of all U belonging to H where U is equal to some C alpha U alpha, say alpha is in F finite. So you take a finite sum of this kind. That means U is a linear combination of not U. Yeah, P is a linear combination of when you say P linear combination finite sum. U alpha in H. So P is a subspace of H. P is a subspace of H. Now P need not be closed. P need not be closed. Okay, because if you are taking you can certainly find a sequence which converges to some element in H which is not in P. Okay, so we take let P closure metric induced by inner product. That is DOM of this is the metric. Okay, this is of course D of, so it's a metric space. Therefore, with respect to this metric, you take a closure of P and designate it by P closure. Now, what you can do is you can get L2A so you take an X belonging to okay. You take the Fourier coefficients of that and you take this collection X hat alpha A. Okay. Now we have already said what exactly is the meaning of this and so on. Now you can show that the mapping X going to X hat given by is a continuous linear map of H and we can show that F is what is this F defined? F of X we define as X hat alpha, which is designated by then F is an isometry of P closure onto this is the theorem that we are going to do. Okay, now this needs some tools to work on this. So in our next lecture, we'll work out the details. Okay, thank you very much. Right, I will once again go into this in my next lecture. Thank you very much.